Yeah, we are just after 12. So, and yeah, let's start talk. And it's nice to see you here. Well, about me. First, my name is Jarek Ratajski, and I'm just developer, wizard, an architect. I mainly do Java, Scala things, browser things. So in fact, I can really do program CSS. You can ask me later how it's possible, but it's possible. And when I have free time, I like to program Commodore 64 from 80s. I work with various technologies, and my daily job is CSS insurance in Lucerne. I live in this nice city under the mountain. On the free time, I travel a lot on bike across the country. Okay, to the point. So this presentation can be reached on this URL. And first of all, disclaimer, it's useless. If you are here because you want to hear some tricks about Java, no, it's not about it. It's about lambdas, but completely scientific, and even though it's basic science. So who knows already lambda calculus? Raise your hand. Oh, quite a few people, quite many in fact. It's more than I expected, so great. And I hope all of you know lambdas. Who knows what lambdas? Okay, there are some people that do know. Okay, by the way, it's not only useless, it's dangerous, because may happen you will find it interesting, and then you risk your life. Not really a real death, soft death. You became no life for a few months or weeks, mostly weeks, when you just dig into this topic. Okay, so the question is what's really Lambda? And this term is 90 years old, almost. The mother, I would say, of this is Alonzo Church. It's a picture from Wikipedia. You can read a lot about him. And he created something called lambda calculus. So what's lambda calculus? It's just alternative maths. You know maths with integer, 2 plus 2 makes 4, things like that. And who knows what's the basic fundamental part of normal standard mathematics? You know? Scream. What? No, normal, not the lambda calculus. Sets. In fact, we always talk about numbers, but the real microcode of the normal maths are sets. But with this approach, there were some problems. It wasn't elegant. It was like very successful, used, but like JavaScript or C++. Not really elegant at all. So that was an idea of Church. Let's make not set, but a function, fundamental content, and let's see what happens. So he created something called lambda calculus, and you can read a lot on Wikipedia. And the problem with it, you will be intimidated by the lot of equations, totally unpleasant screens. Yeah, it looks like math, must be boring. Not, of course. It's not boring, it's only a problem of the language. That's a different language, you are not used to it. At the end, that's a very simple thing, but the problem is language. You need to learn it. Well, not really. Since we have Java, we can make a cheat and try those things in Java, because I assume Java is a very simple language everybody understands. So let's try to recreate what Church has done, basic thing, with Java. So, to the point, Lambda. What is Lambda? Basic fundamental construct of the Lambda calculus. So, if I have only lambdas, and lambda is a function, what this function can take as an input. So, only input. Only lambda. So lambda is something that takes lambda and returns lambda. In our world, nothing more exists. So a function that takes a function returns a function. And I will define it with Java, like this, functional interface, public interface lambda. And very simple interface. Let's make it nicer, almost nicer. And let's play with it. What can we do with such definition? Do you know any lambda I can define that fulfills this? Okay, very basic one. Let's start with something simple. So it's like an empty set in the theory of sets. It's lambda that, let's say, call it L. And I take an x and return x. Very simple. So do you see this well? Or should I make it bigger? This? Well, because I see it's quite small. OK. So it's very simple lambda. You see, it should compile. It's nothing complicated there. It doesn't. Lambda.
You have a typo.
Yeah, exactly. I have a typo. How could that happen? But it happens sometimes. So, yeah, nothing really has happened. Can I do with this lambda something? So, if I do something like system out print ln l, what can I expect? Nothing really sensible. You will see. Moment. It's compiling on my server. Yeah, like identity of object, not really sensible thing. But go back to the code. Moment. I just recreated this thing, and clearly this lambda that was taking argument and returning it, it's in fact called identity. And I can do something with it already. If I have this identity, no more name L identity, it's more meaningful, I can take identity and apply identity to it. So I made something already. I applied function. What does it mean at the end? What does it produce? Nothing really sensible, but it works. And let me now introduce the rules. I will try to recreate a maths, but I will not use here something like integer n plus whatever. I will try to recreate mathematics with the numbers, with a plus function, only using this basic concept of defining lambdas from other lambdas. So in fact, I have only two operations that I allowed. One operation is to define a lambda, and inside of the body of the lambda of this function, I can create other lambdas or apply functions to these lambdas. So now, no real mathematics, no real CPU usage as we know it from Java with integers, whatever, just pure lambda. We'll see what happens. The lambda definitions with application. One cheat. If I am to show it with this system out println lambda, it wouldn't really work because I would see nothing meaningful. So I created a project. It's on a GitHub that analyzes such function and prints what it is. So if I print this identity, I will get the nice mathematical printout of the identity function. You will see how it works. By the way, it cannot work. It's proven that it shouldn't work, but for me it works. I can sometimes play with physics, yeah. So we have this lambda identity, so maybe I will display it for a moment. You see how my system is this smart display, how it works. Yeah. Can we do something with this? Because we have now identity. Can we create something more complex? So let me introduce you funny lambda. Lambda that will be funny. And this lambda will take some A, and what will it create? What can I use? I already have identity. So I will return identity. And let me now print it. I will just print what funny looks like. Yeah, it's like I take some function, and then I return identity lambda. It's written here. This is this mathematical way of showing the lambdas. Yeah, so I can play with that. Maybe to funny, I will apply funny. What happens? I should get, oops, something. One more parent, sorry. It's great. So I can I should get identity in this case. Yeah, it works. So let's do something more complicated. I will do a function lambda that I call a true. And it's defined like this. So in this case, what does it mean? If you don't understand it in Java, I explain it. It's a function that takes an x and returns another function. It's written here. This another function, another lambda, takes an y argument and ignores it, returning x. By the way, always x, y, and are other lambdas, because we operate only on lambdas. So it's not by accident called a true, but for a moment only display. Let me display it for you, how it looks like. So, true. Maybe I will introduce another one. Let me call it false. By the way, you should recognize it. It's the same lambda that I called funny, that takes an x and returns identity function. So, and it doesn't matter how it's named, because lambda is all about how the function works, know how it's named. So in any place I am using, for instance, right now, false lambda, I could use funny. But let's just do it like this. So let me print how all this looks like. Yeah, you see, I introduced two lambdas. One is for me called true, one is false. For a moment, it doesn't make any sense, but if I introduce something more, another lambda that I called end, and I will display it like this. And I will define it like this, and let me display it. By the way, in my displaying function, normally I would display it like display and caps lock. And it would be displayed like all other lambdas using standard symbols x, y, z. Yeah, so you see this end. I defined with p, q, and whatever, and at the end, so p, q. And at the end, I had x, y, and y, but I can make it more nicely for me. I have this utility called webp. So it's only a convention. If you read Wikipedia, those functions will be presented with these symbols, but it doesn't matter. It can be whatever in Unicode is. Okay, so let me now try something. I will create lambda that I call result. I will use this lambda end, and I will apply a false to it, and then to the result of this, I will apply a true, and see what happens. By the way, you see that lambdas can take only one argument, but nevertheless, they can totally behave like functions of two arguments, and whatever number you need, just with a caring. That's the pattern. Let's see what will I get in this result one. I'm nervous. It has never worked before. But you see, I get something like this, and it's exactly the same that I called false. So if I make operation AND with true and false, I get false. That's not a surprise. Maybe let's try something different. True. What happens? Done. And this time, something else. You can recognize this pattern. I called it true before. So this goes easily further. We can skip this part because OR can be introduced very quickly. Just make it quick. So that's how OR looks like. And result 2, maybe I will just make OR with a false and a true. Yeah, and let me display it. Yeah, so you should see at the end OR from false and true, and result 2, I would expect it to be true. Yeah, it is. Okay, to save time, I will not experiment with everything. Lambdas like not can be easily created. In my package that's available on GitHub, I have some utility methods when you can, from a lambda in this definition, recreate Java Boolean and vice versa. So from Java Boolean, this lambda presentation. So just to make the display and playing easier. But let's go to something more complicated. numbers. Because Boolean logic, there was basically two symbols and some operation. That was easy. So let's go for the numbers. And let me introduce this lambda. This lambda I will call 0. By the way, it takes an f and returns identity. By the way, we have already seen it. This lambda we called on the previous slide false. But for a moment, it now plays a role of 0 element. And let's display it. So 0 looks like this. Well, does it look sensible in this moment? I hope, but you can get this code from the presented site or from my GitHub. You can really easily recreate everything I do here. You can even play on my server with this compilation, because at the end it's just a web page, what I'm using here. So let me define lambda that I call 1, and it's this time a little bit different. I'm doing here something nasty. So I take a function f, and then return lambda that takes some x and makes f application x to f. So it's like, yeah, apply this function to the next argument. So this I would call 1. And let me go further. I will create lambda that I call 2. So this time I take f and x. By the way, as you see, numbers are lambdas that more or less take 2 arguments, f and x. And this time I will do application of f twice. It's 2 times applied f to the x. So it will be displayed like this. So let me show it. So yeah, that's the pattern. And easily we can create other numbers. Of course, doing that manually would be crazy. In mathematics, we define successor operation that takes some number n and return something one step bigger in natural numbers. So this is this function. I can even display it if it makes sense. We don't go to the details why does it work. You can track it, you can debug it. But let me now check if it really works by printing successor of 1. So successor of 1. I would expect this should be the same as my defined 2. Let's see. Yeah, so here is 0, 1, 2, and here is successor of 1. Yeah, it's 2. Perfectly works. Okay, so if we have a successor, if we have 0, in fact, it's very easily to create whole natural numbers math. So like, let me define a lambda that would be called, plus. Oh, sorry. Plus, and it's like this defined. This time, you see a lot of arguments because it has to take m, the one argument, it has to take second number possibly, and still has to return a lambda that works the same way as other numbers, so function from 2 arguments. And it's defined like this. We can display it. It would be easy, just a lambda, something displayable. But right now, let's do the math. I will introduce something called a. By the way, I have once again created this cheat function. It's simply to not write f apply too much here. I can create it automatically with my package from cardinals from integers. So I created a lambda a that's exactly in this form as other lambdas here, in which represent number 6, and then second, which represent number 7. And yeah, we can display all these things. And we can, at the end, do something interesting. So we add a and b. By the way, this notation here, plus and a and b, that's called Polish notation. It's standard in functional languages, in some of them. And because of that, it's not really readable. But you need to, okay. It takes a little time to understand and to get used to that. We'll see if plus 6 and 7 really works. And if you are good at counting, you can count those f's here, that there are exactly 13. That means calculation of plus works. So we can do multiplication. I will just skip to the part. Multiplication here it's defined here, and at the end I will multiply a and b, and I will see the result. By the way, I will not make it now. I will not count it. I have another function that counts it automatically in this my utility package. Yeah, so just to avoid, yeah, counting, because I studied maths and it means I'm pretty much bad at counting. Okay, this is this. So you see 6 multiplied by 7, it's 42. Nothing unexpected, it works. So you see mathematics basically work. And we can go with this process further, but let's do something more fancy. Let's do some real programming. Like typical case for this is factorial. So you should know factorial from 3 is 6, factorial from 4 is 24, and 24. Sorry, I'm bad at counting. Nevertheless, to save time, I will just skip typing it. I will go to the final version of this code, and we'll discuss. So predecessor, if we have a successor, we need to also go to from bigger number to a smaller number. For this is this quite complicated lambda called predecessor. We have a subtraction which we can define like this, and now we have some very interesting lambda, if lambda. It exactly represents the if statement in code. It takes a condition which should be one of those previously defined lambdas, so this a true or a false, and then it takes and creates a lambda that takes a t and if, and if the condition was a true, it applies identity to the t. If it was false, identity to the f. It's really, with this construct, we can really call the code that we have in lambda t or in lambda f. Instead of just giving them back, we call them. So it's really like an if statement, but written purely functional way. Then we have this fancy lambda called is 0. By the way, this is behind this is simply this already known lambda true, so false, so takes an x and returns identity. And okay, it's true lambda. It's just utility. It's not real Java Boolean. It's my Boolean for lambda calculus. And we can have even more complicated things like less or equal or things like that. But what is it for? Because I want to create factorial, and I need something that works really magical. The most funny thing you can find on Wikipedia to this topic is something called fixed point operator or Y combinator. It's a lambda that takes another lambda and makes it recursive. So it's really magical. So how it's defined? First, we need some utility function. It's called, I called it autocall. So I take an x, and then I apply it to itself. It's quite rude operator, but nevertheless, it just makes self-application of the argument. Because anyhow, x is a lambda, so it is valid. And why? Combinator is defined like this, with this help from autocall. I cannot print it. There is a reason behind it. But what is now possible is to create recursive function. Why it isn't possible, however, in the pure, without this Y combinator, it's not possible to create recursive function. Because in normal Java, if I define a function factorial, whatever, I can, in the body of the function, use name factorial and refer to this function. The problem is, here everything we have are variables. So if it was factorial, I cannot use this factorial here because it's variable and I'm in part of defining it. I cannot refer to it. It would be a compiler error. So that's the problem which can be solved with this magical fixed point combinator. And what I'm here defining, if you analyze it, is if lambda is 0, so if the number I get is 0, then I return 1. Otherwise, I'll multiply n by here a trick, something, and the predecessor of n. So if it looks like a factorial, but it's not complete because of this, but because of this error here. But what is a g? It's like a precursor or a factory of factorial. And now, if I only use this y combinator and apply g to it, I get the normal factorial. So it's really magical. I took some normal function and with other lambda made it recursive. And now let's just play with it. I will create value a that I will display, and I will just see if the factorial function works on a very simple thing. So factorial from 3. Ta-dam, ta-dam. Yeah, it's 6. You can count it. And it's even possible to use, I don't know, bigger numbers until processor explodes. So you will have right now a lot of ifs. Yeah, like this. So with this utility, I didn't have to count it. It's really, but it's factorial. Okay, so that is the most complicated thing I wanted to show. That's conclude my coding part. Let me just make a summary for this. That was a way to show you that everything that we can do imperatively can be surely done in purely functional way without side effects. It's such limited language. It's not even purely functional in the way you use it in Java or Scala. It's purely functional it's so pure that it doesn't even need a computer to work. It works. It worked in 1930. So, and this means, there is no excuse for you. If something can be or should be done functionally, you should do it. Okay, there is sometimes problem with readability, but if you master it, you can make it more readable as normal lambda calculus. Just a matter of time, of course, not everything, but I would say it's more the problem that a lot of things that should be done functional are not done than otherwise. That is vice versa. I have rarely seen things that were done functional way that shouldn't be. That's not a typical case. Okay, and that was an example. So I showed you that it works, but in fact there is a real proof. Mathematical Church proved in 1937 that in fact Turing machine and lambda calculus are fully compatible. The lambda calculus is Turing complete. So really everything that you can compute can be done with lambda calculus. And thank you. Sources for this are really Wikipedia. I can recommend it. It's really interesting. After this introduction, you can be there. It should be easier for you to understand. There is C# version of this I found while working. It's very nice done blog with detailed explanations of every steps. I was somehow influenced and inspired by the book that I recommend, Emperor's New Mind. There is a little story behind Turing machine. It's quite well, it's controversial book, but it's quite well describing the topic of Turing machine and things like that. And Lambda visualization is a GitHub open source project. You can use it if you want to play it. And this presentation is under this URL. If you want to ask me something, we don't have right now time, but I am free for you. Anytime. Okay, thank you.